Bismillahirrahmanirrahim. Good afternoon, everyone. Our lecture today will talk about the important thing in the semiconductor. Like we know, we have two kinds of doping. Like I said before, we will talk about the twice doping of the semiconductor. I will start from p-type doping solar cell. At first, let's know what does mean p-type doping and what does mean doping, what has the appropriate meaning to it to can understand all these lecture. Like I said before, we have two kinds of doping. P-type, it's one of these two kinds of semiconductor. It is produced by adding one atom, such as boron or gallium. And I will explain that at the next slide, why we selected boron or gallium element, not select another element like phosphor. Let's explain that have one less electron in their outer energy level than does silicon. Outer energy level, that's mean the last shell, the last orbit. Let me use this diagram, this simple diagram, and at the same time, it's very important to can understand this subject. Like we know, silicon has 14 electrons. At the first one, just 2 electrons. The second, the last one, 4 electrons. Now let's go to this diagram. Here, these 4 legs explain to us the 4 electrons at the last orbit to silicon atom. And at the same time, boron has just 3 electrons at the last orbit. I used the blue ring to show the electrons at the last orbit. Yes, now let's focus on this spot. Here, boron has just 3 electrons at the last orbit. Like we know, atoms like that need 4 legs. Let's imagine this atom like animals in our environment. Like we know, any animal need most of these need 4 legs to can walk, run, stand, something like that. Let's imagine this boron-like animal need 4 legs to can walk and stand or something like that, some activities like that. Now, the purpose of these 4 legs will be to make this atom to can reach the stability situation, okay, like silicon. We must this atom can do that by take another electron from another neighbor, from another silicon atom's neighbor. The boron atom has missing 1 electron, like I explained before, to complete the 4th covalent bond. That means here any electron show to us covalent bond. Silicon has 4 electrons at the last shell. That means has 4 covalent bond at the last shell. To complete the 4th covalent bonding to reach the stable state. Now let's complete. Like we know, phosphorus has 5 electrons at the last shell, not like the boron or gallium. And because this feature, we will use this element with n-doping. I will explain that at the next lecture. What is the p-type doping and what we will use it with what and why? In p-type doping, boron or gallium is used as the dopant. Dopant, something like, we can imagine something like drugs to can do some crazy thing, some activity to make this atom reach the stability. These elements have 3 electrons, like I said before, in their outer orbit. When they are mixed into the silicon lattice, they form holes in the valence band. Let's imagine what that means. Holes, what that means, what the appropriate definition to this word. Hole, that means the empty space. The electron will created it after jump from band to another band, from the valence band to the conduction band, trying to reach the conduction band. Okay, this empty space, we will call it the hole. Silicon has 4 electrons, and for at the last orbit, like I said before, this I explained this diagram. Here, let's talk about the room temperature. At room temperature, T equals 300 Kelvin, this is satisfied by 1 electron on the neighbor silicon atom. This diagram, I think, is better to understand this idea, because it is the most important idea, is the doping, p-doping or n-doping, this idea. Here, the 4 legs to silicon, here 3 legs to boron. Boron will take 1 electron from the silicon atom to can reach the satisfied situation, to can reach this situation, this figure. Here, boron, I forget to draw another line here. I'm sorry. See, boron here, after take this extra electron, will has 4 equivalent band, can build strong wall with the other silicon atoms, with the other neighbors, can say like that. Here, the silicon will miss this leg, this electron, will denote this electron, will send it like donor to can do the appropriate emergency to his neighbor, boron. After this process, the boron atom will be negative. Why? Because actually this boron, this atom gain extra negative charge, because we know what the charge of electron, actually it's minus, it's negative, because that the boron will be negatively charged because it is gain extra electron from his neighbor. Let's create appropriate definition. What does mean acceptor atom? Acceptor atom is the boron atom accepted 1 electron from another silicon, I mean his neighbor, earn or gain another electron, extra electron from his neighbor. When 4 equivalent bands are completed on boron atom, like I say, I'm sorry again because I forget it, draw another line here. These are the equivalent band. By this situation, by this donor electron, the boron can build great and strong wall to can catch the other silicon atoms near from him, from these 4 sides. Okay. After that, let's focus on the simple function, but at the same time, it is very important, because like we know here, N, that's mean the concentration of electron on the conduction band, P here the whole concentration at the valence band, and Ni equal, that's mean intrinsic condition square, intrinsic square intrinsic condition at p-type and n-type doping. N didn't equal P at all. And we will discuss why at the next slides. Like I said, P is the concentration of hole at the valence band. Here, P type doped. We can, by using, why I say this very important question to us, because by using, when I will select this B type or N type doping, I will can know the concentration of electron in the VP in the CB and the whole concentration of hole at the VB. Okay. Let's take this something like example. Here, P type doped. I selected that. Okay. Let's imagine I have a question and I know which kind doped here. Let's say is B type doped. That's mean P equal density of acceptor atoms. By this situation, I can know the concentration of electrons at the CB. That's mean N will equal intrinsic semiconductors square divided on P. At the same time, P equal NA. That's mean square intrinsic semiconductor divided on P equal concentration of electron at the conduction band. And I will do the same process at the N-type doping, but I will change some simple things to can calculate the concentration of hole. Okay, this is P, that why P equal NA. If we facing a question like that, why concentration of hole at the valence band equal the density of acceptor atoms at the P-type doping. Because here the concentration of holes B will increase. Oh, that's great, will increase, but why still P equal NA? At the same time, the holes will increase. Because without creating any free electrons in the conduction band. This is the important few words to can answer a question like that. But now let's go to this diagram. This diagram will be great to can do comparison between N-type doping and P-type doping. And like we say here, the ions, positively ions, minus ions, explain to us, show to us the Na acceptor or N donors or donor. And this place will show to us the natural region, natural to N region and natural to P region. And the charges will be here. And this D belong to holes, here belongs to electrons. This great figure explains to us the really meaning to the hole by this imaginary figure. Okay, like I said before, boron need 4 legs to can reach the stability situation. Here, I use the yellow ring, yellow color, I'm sorry, ring in Turkish language. 1, 2, 3 electron at the last orbit to the boron, but at the same time need 4. Each electron from all these 4 electrons has 4 electrons at the last shell. 1, 2, 3, 4, except the 4th one. Like we say, I use the black color to show the acceptor impurity. creates a hole, to create this square, this black square show to us the hole. What that's mean? That's mean here the electron is taken from another atom, silicon atom, and because that still be like that, empty, and after that this boron will try to take electron from the another neighbor to can complete this wall, to can complete this overlap between these 4 electrons around it. This important note, since boron accepts electron from neighbor silicon atom, it is equivalent to accept 1 electron from the valence band. That's equivalent to accept 1 electron, but exactly just from the valence band of silicon, not conduction band. Therefore, there exists a free hole in the valence band, even there was no electron transition. Let's be this important word, this important to us to can answer this question very well. There was no electron transition to the conduction band. After a few moments, what I say, 1 electron from the valence band of silicon will accept. Here, we'll focus on the same meaning by saying no electron transition to the conduction band. That means the process in p-type will be around the valence band. These acceptors levels accept electron from the valence band and therefore create a hole in the valence band. This diagram complete to us the idea here, because here we're missing 1 electron. What we'll do, this electron will start to jump from atom to atom, atom to atom. After that, we'll create to us free electron. And now let's focus on this note. The vibration of silicon atom provide enough energy. To what? This enough energy to realize a hole from boron side into valence band, specifically at the valence band. We will not facing here extra communication, extra process at the conduction band. We will focus on this spot, valence band. For this reason, doping silicon crystallium with well element of group 3 is called p-type doping. Because like I said before here, p illustrate to us the holes, and by this by these holes, this will be a positive charge doping, and at the same time holes illustrate to us 2 hole, and we selected appropriate letter to explain this process by using P, because that we say p-type doping. Now let's focus on this simple diagram. Here, like we explained together at the last lectures, we have 2 important energy band. Actually, not 2, 3. At first 3, and after that we will study more and more. At first we have valence energy band, this EV, and after that this will be at the first of this diagram. EC will be the upper line this diagram. EC, that's mean conduction energy band, and at the middle will be EF, that's mean Fermi energy level, and another situation, extrinsic energy Fermi level. But now that's not our lecture, that's not our target. Let's focus on this. Here, what that's mean EA? EA, that's mean the acceptor energy band. And we facing here something like condition. This energy acceptor band must be near from the valence energy band. No way, this fact. EA must be near from valence energy band. And here, this hole, this electron will try to jump to the near energy acceptor band by creating a hole at the first line, I mean EV. Energy levels of acceptors atom will be created in the energy band gap at the middle between these two lines, EV, EC, to the end last point at the EV. All this space will mean to us the energy band gap. That's mean the semiconductor will be isolated until the applied electron be equal energy band gap or more than. That's another words about another topic, okay? But has a relationship because that I noted it. Now, like I say, the energy acceptor band will create inside the energy band gap. All these you must note my mouse moving. Okay, let's go to another slide. Here, let's take this example, this question. How the p-type materials increase in the conductivity. How the p-type materials increase the conductivity. It increases the conductivity by what? Let's know by what. By increasing the number of holes present. That means the concentration of holes will change because the p-type materials will increase the conductivity by increasing the number of holes present. The same diagram here, but I put it the extrinsic energy Fermi level and the Fermi level and the p-type, like I said, be near from the EV valence energy band. That's condition. And at the n-type will be upper, near from the conduction energy band. But we have another condition. EF Fermi energy level must be upper acceptor energy band. That's it. I finished my lecture. The next lecture I will talking about and explaining the n-type doping information. Thank you about your watching. I will see you at the next lecture. Gelecek derste görüşürüz arkadaşlar. Kendinize bakın. Eyvallah. Let's start this recording.